Hi, everyone. In this presentation, we developed a process to determine when machine learning is applicable in robotics. We identified key algorithms to use and determined a good algorithm for decision-making in robotics. And we also performed several case studies of this in the context of First Tech Challenge. So we are part of the First Tech Challenge team, Batteries in Black, and we've been a team since 2007. Throughout the course of our time, we've attended the World Championships 5 times. And in 2015, we won the World Championship Sensor Savant Judges Award for our high quality usage of sensors on our robot. So First Tech Challenge is part of the FIRST program, which stands for Inspiration and Recognition of Science and Technology. First Tech Challenge, or FTC, is a competition for high school students. Students design, build, and program their own robot that must complete tasks outlined in each year's game. It's an opportunity for real-world experience of engineering. So in the FTC game, robots have many different components that allow for decision making, including software, sensors, a controller, and an actuator. So in the FTC game, the robot is controlled by an Android smartphone, which receives inputs from sensors and sends commands to the actuators. And these Android devices are programmed using Android Studio and FTC SDK, which allow the phone to communicate with the various motors and sensors. One Android phone is connected to the joysticks, which is used by the human drivers to control the robot, and the other phone is on the robot and communicates with the other phone using Wi-Fi Direct, and also controls the robot. So there's 2 phases in the game. There's a user control phase where drivers can use the joysticks to control the robot directly. And there's also an autonomous phase where the robot must independently move and use pre-programmed instructions and decisions on its environment to score. So some example of decisions it must make is choosing between 2 different paths, stopping the robot from tipping when it's moving, and determining the position of a randomly placed object. So as you can see, the accuracy of decision making is extremely important in the game. So there are a lot of challenges in decision making during the game. So in the game, the environment is constantly changing due to the motion of other robots and game elements. And as a result, decision making must include sensor data in order to make informed decisions based off of current environments. Additionally, because so many factors change throughout the course of the game, the decision making must be thoroughly tested to ensure that the robot can consistently make correct decisions.
All right, so when we first started looking at this and seeing that there was difficulty in decision making, we wanted to take a scientific approach to this. So we wanted to say, okay, hey, let's collect some data. Let's see how we can improve the performance of our robot. So what machine learning does, as you can see up there, it gives computers the ability to learn without being explicitly programmed through data. So the ultimate goal was that our robot would be able to learn from data and it would be able to perform robustly under differing environments. So as you can see up there, how we provide data to the robots is through something called features, which are essentially variables. And I mean, features can be any sort of thing. Like if, let's say your problem is, it doesn't necessarily have to be in the context of robotics. Let's say your problem is you're trying to predict the price of a house. Maybe your features is like the square footage of the house and like how many rooms there are in the house. Those are just different variables. And getting good features is really important. Arguably, it might be even like the most important part of creating a machine learning model. For example, there's a certain algorithm called the perceptron algorithm. That algorithm is guaranteed to converge on an optimal solution if you get like good features. And for example, the field of computer vision, it was mainly driven by hand engineering features for like a very long time until something came around called deep learning, which you may have heard about in today's world. All right. So this chart kind of shows how we decide whether or not to use machine learning in the problems that we face while programming our robots. So basically the 2 branches in there are dealing with if there's just inherent sensor issues, like your sensor is just not accurate enough or is unreliable, machine learning can't really help you with that. And we also need to be able to test the performance of our algorithm. So that was another key requirement. So those are basically the 2 decisions that we have to make. Okay, so we wanted to be able to test our, as I just said, we wanted to be able to test our algorithms. So what we did is we did something where we partitioned our data into training and testing sets. So if you're familiar with machine learning, that's it's what it's about is you provide some data for the robot to learn off of, and then you provide some data where you're testing how reliable your algorithm is. So the data that the robot learns from is called your training data set. And generally, the reason why you have something called both a training data set and a testing data set is that you want to avoid two big problems called underfitting and overfitting. So underfitting is a problem where your model is simply not complex enough to deal with like the environment that you have. So like maybe you're trying to fit a linear model to something that's actually quadratic. And the opposite problem is something called overfitting, where your data learns the training data too well and it is not able to generalize well. So maybe like you have like a sixth order polynomial when you're trying to fit to quadratic data. So both of these are really big problems. And the way you solve this, or the way some ways you can avoid this is by making sure that your algorithm has high accuracy on both a training data set and a test data set. So after we verify that the algorithm is good on both training and testing data sets, we implement it into our main autonomous routine. And there's another step that you can implement called a cross-validation step. So often in machine learning algorithms, there's these things known as hyperparameters, which deal kind of with how the algorithm learns. So in order to tune these hyperparameters, there's a method called cross-validation where you kind of split your training data into different parts, and you take one part to be a validation fold where you check the performance of the algorithm depending on the value of the hyperparameter, and then you cycle through which part of the data is your validation fold, and then you average your performance to get good hyperparameters. But that's a little too deep for today, but we didn't actually use that in our project because we found that it wasn't really necessary. But that's something that definitely you should look into. All right, so the two big kind of problems in supervised machine learning are classification and regression. So classification involves identifying to which category something belongs to. So let's say your problem is like you're trying to detect if an email is spam or not. So that would be an example of a classification problem. You provide the algorithm with the data in the form of your email, and then it's trying to see if it's spam or not. Regression is something different where you're kind of trying to predict the value of some other variable. Like maybe it's like you're trying to predict the price of a stock based on different features. So we found that for our purposes, we were really more concerned with classification. I mean, there's definitely cases where regression would be useful, but we found that classification was generally where we needed to focus our efforts. All right, so up there I have 5 different classification methods. So yeah, I'm just going to briefly go over kind of what these are, and you can definitely take a look into them. The one that we're going to be focusing on mostly today is actually the logistic regression one. So, but the other ones are also just, they're widely used in industry and things you can look into. So the logistic regression classifier basically fits a sigmoid function to your data, and it like returns a probability that your data belongs to a certain class. Then there's the support vector machines algorithm, which is really well known in industry for being like probably the best out of the box classifier. And it's known for also finding what's called like the optimal separating hyperplane between classes, which is basically like math jargon for saying that it like separates it's supposed to separate your data with the maximum margin. And this also, it doesn't necessarily have to be a linear classifier. You can use something called the kernel method to make it work when your data is not linearly separable. Then there's the naive Bayes algorithm. That is basically uses Bayes' rule from probability to find the distribution of your data. Then there's decision tree classifiers, which use decision trees to map feature values to classes. And then there's neural networks, which you may have heard about. They're becoming really popular. They're used in deep learning, which lots of companies are doing research into. All right, so yeah, as I mentioned, we're mainly going to be talking about logistic regression. So Probably the biggest consideration is that it was really easy for us to program, and it wasn't hard to get working. And it's also really easy to interpret what it's returning, because it's returning a probability that your data belongs to the class. And there's something that's a little bit. There's another benefit in that if your data is kind of noisy and not cleanly separated, logistic regression works pretty well. Actually, in some cases, better than, for example, the support vector machines. And you can also like adjust, like maybe since you're returning the probability that your data belongs to a certain class, you can adjust the threshold. Like maybe you say, like generally you'd say if probability is greater than 0.5 is going to be this class, but maybe you could adjust that threshold if you have something noisy. So as far as implementation, in industry, I think what's most frequently used is probably Python, and there's something called the scikit-learn library that's really used in industry, and it's really easy to get working. And then especially now with there's this craze about deep learning, that's people use libraries like TensorFlow, for example. And then if you're more familiar with R, I believe there's like the Caret package that you can look into. And then actually how I got into machine learning was by taking Andrew Ng's course on Coursera. And so that course is actually taught using Octave or MATLAB. So a lot of our programs here were actually done through Octave or MATLAB because it's really easy to figure out how the algorithm is working when you write them in Octave or MATLAB. But I'd say like if you're trying to use it for like an application, probably Python is more scalable.
Yeah, so Anjuman kind of mentioned why machine learning improves decision making, and so I'm going to talk about 3 case studies that we did in the context of robotics that kind of demonstrates how machine learning can really improve the accuracy of this classification. And so the 3 case studies that we're presenting, the first is using an IR seeker, which is an infrared sensor that can detect IR signals based off of a beacon that emits this signal. And so the first case study is looking into classifying which of 3 positions the IR beacon is located into. So this is classification because you're classifying this value into one of 3 options. The second case study is similar. We're using, instead of an IR seeker sensor, a color sensor that can detect different signals such as alpha, red, green, blue, hue, saturation, and value. And using these values, we're looking to use machine learning to determine the color of a beacon. So it can either be red or blue. And then finally, our last case study is utilizing the internal sensors within an Android ZTE Speed phone, which has many internal sensors like the accelerometer or the gyroscope. And so using these sensors, we're looking to determine when the robot is tipping. And so how we do this in the context of robotics is we separate tipping into 5 main categories. The first is not tipping at all, it's just stationary. And then the other 4 are tipping in each of the 4 directions. And so obviously this is pretty useful in robotics, as many times the robot is placed in precarious situations. Maybe you're not able to have human control. So the robot really needs to know what is its current state, is it tipping or not, in order to take the necessary steps to avoid fully tipping. So as I mentioned, the first case study is using an IR seeker, and that's right here. And so this is really used to determine the position of an IR beacon, which is one of 3 places. And so the reason that machine learning is so important in this application is that ambient lighting conditions generally change between where the robot is used. And many of those emit IR signals. And so that can interfere with the data. And we actually found that if we did not use a machine learning algorithm, at many instances it was difficult to classify which of the 3 positions. Although in testing it worked fine, when we applied it to other applications, it did not work as well. And so that's why we implemented machine learning. And so what we did is we mounted the IR sensor, which I've shown right here, onto a servo, which is a small motor. And we rotated it into 45-degree increments, so 0, 45, 90, 135, and 180 degrees. And so this allowed us to sweep the general surroundings and collect data from many different locations. And then within the IR seeker, there are 5 sensors that can tell us what the IR signal is at 5 different zones. So each time we sweep, we get 25 data points. And during testing, we repeated this process 100 times to get 2,500 data points. And then furthermore, we did this for each position of the IR seeker, or of the IR beacon. So we could get data for what the data looks like for position 1, 2, and 3. So in total, that resulted us in having 7,500 data points. And so in testing, when we test to see what position the IR beacon is in, we simply have to do one sweep, that 5 rotations of the servo, and then that is an input into the machine learning algorithm, which then gives us the probability of it being in one of those 3 categories. And like Anshuman mentioned, we used a logistic regression method. We use a one versus all regression method. So we use 3 sigmoid functions in order to find out which category it's in. And using the machine learning algorithm, even under varying lighting conditions, which we tested for, we still had 100% accuracy. So the second case study is using a color sensor. And so similarly, we are trying to use machine learning to classify a beacon into one of 2 options, in this case, red or blue, using this color sensor right here. And so that's randomly assigned. That's variation in the environment. And so what we do is we collect the various data from the sensor. So as I mentioned, RGB, hue, saturation, value, and alpha. And using this, these are the different features into the machine learning program. We can determine what color this beacon is in. And so we used 4 data sets for training and 4 data sets for testing. So this is how we partition the data. And we average each training data set over time. So we'd collect data for a certain amount of time and then average that data. And then we tested under 4 different lighting conditions. Each of the different data sets were under a different lighting condition. As you can imagine, ambient lighting conditions in this case also matters. We're looking at the color of objects, and brightness and other factors like that can greatly affect the accuracy of a sensor. And so under different lighting conditions, including dark, adding spotlights, things like that, we're able to really simulate what changing environment would really look like. And so, again, you can see the column matrix right there. This really just has the different coefficients for the linear combination of the different features. So the first is just a constant, but then each one afterwards is multiplied with each feature. So the second one, for example, you'd multiply that by the alpha value, and then add the second one multiplied by the green value. And so you can keep doing this and produce a number. This is then plugged into that sigmoid function, returning a probability. And again, when we tested this, even under varying lighting conditions, we had 100% accuracy, determining red versus blue. So our last case study is using the internal sensors within a ZTE speed phone. And so it can be generalized to different phones too. So we have a Motorola phone right here. We tested it for both. And basically, in the autonomous period, in the first tech challenge game, we have 2 phases, like Jenny mentioned, the autonomous phase and the teleop phase. And during the autonomous phase, the robot operates completely on its own. We are not allowed to use our joysticks. And so the robot is climbing over things, and it has a high probability of tipping. And so the idea of this case study is to kind of collect data from the phone, which is attached to the robot, and understand if the robot is tipping, which would allow it to make the necessary changes. And so we partitioned the data. We used 5 different phones for testing, for testing and training, and 3 of them were for training, and 2 of them were for testing. So that's a 60% and 40%. And we collected the various different sensor values. So this actually included a wide range of sensor values within the phone, every single sensor that is reported. What we did do is remove different features that weren't related to our problem. For example, the proximity sensor on the phone does not really tell us much about if it's tipping or not. So that was removed after we carefully analyzed if any of these would have a correlation with tipping. And so again, we used the multi-class classification. And then when testing, just like with our other case studies, we tested it while simulating each orientation. So in the case of this orientation determination case study, we would measure data while the robot is flat on the ground, while it's tipping in one direction, and in all the other directions. So this gave us 25 different data points when training. And so the data is kind of shown here. This is when we've reduced the data. So we've cut out all of the unnecessary data. So you can see here we collect data such as the magnetometer, orientation, and accelerometer for each of the 5 positions. And so this gives us a lot of data that we can then input into our machine learning algorithm. And so we can see the confusion matrix, which is a common way of demonstrating the accuracy of a machine learning program. As I mentioned, we had 3 phones that were used for training, and then these are the 2 phones that were used for testing. And so when we tested at orientation 1, it was predicted that it was at orientation 1 for both phones. And that was true for every single orientation. So because there were no deviations from the diagonal, we can see that it again performed with 100% accuracy, which was not the case when we didn't use machine learning. So we just showed three different case studies of using machine learning in the context of robotics. The first was using machine learning to determine which of three positions an iris seeker was located. The second was using a color sensor, and the third was to determine if the robot is tipping using the internal sensors on a phone. And there are a few more applications that this can be extended to using the same backbone of machine learning. And so the first is using neural networks to tune PID controllers. So PID is a really common control system loop used in robotics very frequently. Basically, it allows it to maintain a certain power level even with deviations. So for example, we've used that when trying to drive straight. Sometimes some motors are more powerful than others, and it might kind of veer off course. So it's important to use a PID controller to make sure that you're driving straight. But something that PID controllers require are PID constants. This is the proportion constant, integral constant, and derivative constant. And many times these can be really difficult to find. They require a large amount of testing, many hours, and when you change certain parts, like if you replace a motor, these constants can vary, requiring you to test that again. And so machine learning can actually be used to tune these PID constants by, again, taking training data, running the robot, determining the success of that run. Maybe you measure that by the angular error after you run the robot. And then that can be used to kind of minimize that error by tuning the PID constants. And so that's something that we're actually working on right now, but would be an extension using similar principles to what I just showed. Reinforcement learning is an up-and-coming field in machine learning. And it basically looks at assigning a reward to a certain action that a robot takes in the case of robotics. So if you had a really complicated arm, a reward could be successfully moving some object or moving the arm correctly. And so using reinforcement learning, you can kind of train the arm to do correct motions to do a certain task. And then the last one that I think we're familiar with machine learning is object recognition. That's really common, especially like with phones trying to detect your face or things like that. And so again, machine learning can be used to determine what's a human face, what's not, and other objects like that. And of course, the camera would be the sensor, and the different pixels would be the features.
So, in conclusion, we investigated utilizing machine learning to improve decision-making quality in the context of robotics. So our key contributions were that we developed a process to determine when machine learning is applicable in robotics. We identified key algorithms and determined a good algorithm for decision-making in robotics. And we performed several case studies in the context of the First Tech Challenge, which is the competition we perform in. So now we're going to demonstrate our robot.
So we have a few things. The first is we've loaded the tip detection algorithm into our phone. And so that uses the internal sensors within this to determine when it's tipping. So we're just loading the phone. Basically, we have one Android phone here that's connected to joysticks. And then the other one is connected to all the different components of the robot.
You want to do the tip detection or driving around?
Should we start with tip? Or,
Okay.
Sure.
Sure.
Yeah.
It's kind of hard to see this.
Okay, that's true. So right now it says not tilting, basically because it's on the ground. But if you
If I tilt it
forward, it says tilting forward. So you guys can come up afterwards to see. But in essence, it's very quick. It just needs to see a few readings from the phone, which is almost instantaneous, to determine when the robot is tipping. So the next one is we're going to drive it around. And you guys can come up and drive it around if you'd like.
We ride it?
No. And so this is just using different signals from the phone to the controllers, which are then connected to the robot, which gives it power.
Does anyone want to come up and drive this?
And we can.
Totally fine. You're not going to break it.
What's the new challenge for this year?
Yes.
We actually have to shoot these wiffle balls into like goals. It's kind of like basketball, kind of, I guess.
Scale down a bit.
Yeah.
Wiffle balls and the goals? Okay.
Mm-hmm. Yeah.
Were you guys part of the basketball competition a couple years ago?
No, that's actually the program that's above us. There's like First Robotics
Okay.
competition. So they build a bigger robot, so we
Yeah,
got
that one.
Yeah.
Very cool.
Any questions?
I have a question.
Yeah.
Why did you test with multiple phones? Is that part of the competition?
So yeah, we just tested with a lot of phones to make sure that we didn't do any algorithms specific to one phone. We wanted to make sure that variations between phones didn't affect our readings. Usually, yeah, we do have multiple pairings of phones that we use, but we found that the variation between phones wasn't that too significant, especially if we calibrated them beforehand. Yeah.
Are you sure you guys are just in high school?
Good job. Actually, I have a serious question. So I wanted to ask about mixing of approaches. Did you ever consider mixing some stuff like fuzzy logic in with some of the other approaches to see where maybe like solving a sub-problem might have been done better with one kind of family and then solving the others with the different kind of partitioning things up?
Yeah, so I'm not too familiar with that, the fuzzy logic thing, but yeah, I definitely, I guess like it was a tool that we were kind of like learning about, and we were just like, oh, hey, when all you have is a hammer, everything looks like a nail, right? So we were just like, okay, let's go apply this to this. Yeah, there's definitely probably better solutions for some things, like maybe for the object detection, I think there's definitely, like, you don't necessarily need to take a machine learning approach. And there's actually something called like SLAM, simultaneous localization and movement, that I don't think, that method doesn't really use machine learning, but that's like a good method that you can try using a camera for tracking things while the robot is driving around. So definitely something we would look into, but for this, yeah, we just decided to try machine learning.
I have a question for you. How do you, besides see testing changing over the next 10 years, especially when you introduce machine learning, neural networks? It has a 2-point, basically it's a whole way of thinking of neural networks outside the Van Neumann paradigm. What do you see the changes? Where do you see the changes? There's a QA.
I don't know. It's actually interesting. Our actual robotics competition has evolved. We used to use NXT bricks, like the Lego system, beforehand, and that was extremely slow. We really couldn't collect data, and so the software sophistication that we had was really limited. But then we actually transitioned to Android phones a few years ago, and because of that, we're able to collect a lot more data. So even with our robotics itself, we were only able to do such a project because we had, improved phones and ability to collect a lot of data. So I guess one aspect that's really coming about is that we have a lot of data, and it's important, we can't manually go through all of it, so it's important that we develop machine learning algorithms that can kind of derive meaning from them when we really can't.
And I think something that's been happening kind of in the recent years is like the reason that neural networks have been gaining so much popularity is because now we can compute so much faster. Like for example, some of you may have heard about the robot or the computer that Google made play Go against someone using machine learning and specifically something called deep reinforcement learning. So it took like weeks for them to train that algorithm, but like in like years ago that wouldn't have been considered possible at all. And so like I think actually neural networks kind of fell out of popularity for like 20 years or so until they kind of started making a comeback as people realized we now have the computational power to start using them in practical applications.
With the reinforcement learning, what constitutes a reward for a robot? I mean, is that what the reinforcement learning means, or how does that work?
So I guess it's kind of difficult to choosing the reward is kind of difficult. So like I guess what we were thinking about and some projects that have been done is like when you're controlling like a complicated arm, maybe the ultimate reward is like how close you get to like maybe picking up something. So that I guess that would be kind of the reward.
In machine learning algorithms, especially classification ones, you have to have both the data that you're testing and the results, whether it was a pass or a fail. How did you guys, or did you collect your data manually and enter in a pass or a fail when you were creating your data sets, or how did you guys go about that?
Yeah, so since we had kind of limited amount of options, it was actually pretty easy for us. We kind of wrote a program that would collect the data, and then we said, okay, we're doing red right now under these conditions, and so that was kind of the parameters into the program. And so it was pretty easy to just kind of change it from red to blue. That was pretty easy to change in the program, but that was something that we manually kind of wrote after the fact.
Do any of you plan to attend college?
Yeah.
Definitely.
Have you started filling out scholarships through First Coast yet? I think you should.
I think we know, like, we went to our last competition at St. Louis. We were kind of talked with a lot of the representatives there about scholarships.
Yeah, and a lot of colleges come to the competition and just hand out brochures about the opportunities they give and the scholarships they give to people who participate in FIRST.
With FIRST, they usually have on the 1,000 or 2,000 scholarships that go unclaimed every year. So make sure you're filling out scholarships early.
So what college you guys dreaming
I think for most of us, I think we're gonna apply and kind of see where we get in.
Yeah.
It's not a decision we've completely made yet.
Yeah.
about? For this type of thing, MIT will be good.
Anyone want to drive the robot? Okay. All right.
Good job,
Ready to
guys.
come up?